Hello, everyone. Today is March 18th, 2022. I'm here today with Ran Levy. Ran is a podcast host and software engineer. Thanks for coming on the podcast, Ran.
Thank you very much for inviting me, Kruj.
You're welcome. So, how did you get into software and what started your technical background?
I started as a hardware engineer, electronics engineer originally. I was a board designer for something like 10 or 12 years. And at some point, and software wasn't really on my mind. I didn't even like software initially. But at some point, I had a week off work and I had nothing to do. And I've said to myself, you know what? I've heard about this language Python, which everybody was talking about for some reason. And I said, I've got to learn what's everybody's talking about. And after 3 days, I fell in love with programming, really enjoyed myself, and went to my boss and said, you know what? I want to change my career. And then from then on, I programmed in Python and also did FPGA programming, which is on the boundary between software and hardware, you can say.
What does FPGA stand for?
Field programmable arrays. These are kind of programmable chips using VHDL, which is the I think the analog of assembly in programming. It allows you to program logic gates in the programmable gate array, the FPGA, and using it, you can build whatever you like in hardware. I mean, memory arrays, CPUs, controllers, whatever you like. So it's fun. It's like you actually program the hardware. Uh,
That's
one of the, one of the least known, I think, fields in programming, but one of the most challenging, I think,
what makes it challenging.
because firstly, because it's very, very low level. We're talking about logic gates here. We're literally programming the basics of computer microcontrollers. And secondly, because the rules governing hardware are a bit different than software. For example, uh, everything is in parallel. Everything happens in parallel inside of a chip, of a CPU. So you've got to think in parallel, which is something that I think most software engineers don't do in their day-to-day lives. I mean, we're thinking in linearly. Something happens and then something else happens. Programming hardware means you've got to think parallel, which is rather challenging, but also great fun.
What do you mean by parallel?
Um, let's say, for example, a standard loop in programming, a for loop. You assign I equals 0, and then you do something. And then you go back to I equals 1, and you do something else. That's the normal way software works. When you're talking about logic gates and the hardware mechanisms, then everything practically happens at once. You've got, for example, two separate logic gates. Each one could be a different, totally different position inside of the chip. They're both working simultaneously and getting activated when the clock of the CPU rises. There's the basic of hardware. Everything is controlled by clocks. And when a clock is activated, all the logic gates in the system are activated at the same time. So you have to think um, like horizontally instead of vertically, as in software. It takes lots of time to get used to, but once it works and you get the hang of it, you feel like you've got superpowers because everything happens so much faster than in software. I mean, In software, a single command or a micro command could take, I don't know, one thousandth of a second. When you're talking about hardware, everything happens in nanoseconds. So you can do lots and lots of stuff really down in minute scales.
Oh wow. What's the reason for the time difference?
Because you're working directly with the metal, with the bare metal of the design. You're actually working with hardware. Once you're done programming, you load the design onto the FPGA chip. It's a specialized chip, and from there on, you don't control the design. It works on its own. I mean, you don't have any control. You can't stop it, or you can't, pause it like you do in software. So, and everything happens in terms of the clock rate of the CPU. And you know that like Intel's and AMD's chips work in gigahertz, which means there's a clock cycle every few nanoseconds. And then that's the same with FPGAs.
Okay. And what types of devices would we find FPGAs on?
Right now, they are pretty specialized. Mostly industrial and military designs, which because FPGAs are more expensive than regular ASICs, regular, I mean, CPUs and microcontrollers. Being programmable makes them a bit more expensive and a bit more energy consuming. So it's not for for the consumer market most of the time, although everything is getting better and better all the time, and the potential, I think, of using FPGAs in commercial products is very interesting because, say, for example, right now we've got phones, for example, we've got a CPU inside of them, and that CPU is frozen, so to speak. It can't change. The hardware itself cannot change. Imagine that the software could be quote unquote liquid in nature. You could program the CPU to be something else, maybe a stronger CPU and more energy consuming if you've got some application that requires like heavy computing, or you can reprogram it to be a weak and energy conserving device if you've got an application which doesn't need lots of energy, so you can save the battery. So it gives you a kind of new flexibility, but right now it's a bit too far in the future because it will make our devices more expensive.
Okay. Wow. Do you expect that to happen to
probably
FPGAs?
within probably within 10, 20 years, I think we can really start speaking about it, because I think that Intel bought a major player in the FPGA market a few years back. So it seems as if Intel has got some, plans in that direction. Right now, I think it's mostly being used in the commercial world. It's probably mostly used in AI because you can reprogram the chips to be more effective for AI computations alongside GPUs. Um, but who knows?
Okay. But this AI would be on an industrial scale currently because FPGAs aren't implemented on the commercial scale.
Yeah, mostly right now in industrial applications and military applications. Probably more commercial applications in the future. Probably.
Okay. So your background before you got into software was hardware. What types of hardware technologies and were you working on, and what type of hardware engineer were you?
Mostly military equipment, sort of of devices. I did board design, which means creating all the electronic boards inside of various equipments. working with Intel's chipset, most of the time graphics, NVIDIA's chipset, creating the electronic boards that actually you place the chips on. Um, it was an interesting experience, but at some point I figured that it's a dead end in terms of my career, because I started like in the early 2000s, and even back then computers were starting to get so much better at designing these systems. And also most of the exciting stuff was happening inside of the chips and not on the board itself. So it felt as if I'm placing Lego bricks, and it wasn't. I mean, it wasn't very challenging. I think challenging enough, and I figure that it will, if it's not challenging right now, it will probably be even less challenging once we have more sophisticated software tools, and then my role as an engineer will be reduced to like printing out what the computer says and just doing what the computer says. I want something a bit more challenging.
Yes, that I actually wrote an algorithm and I studied. I don't know if it's the same aspect, but is it called floor planning? Uh,
Floor planning is for when you're designing chips, when you're designing CPUs, etc. And it's also hardware engineering in a sense. It's almost the same with board design. Yeah, very similar, except that
okay,
you have to more think about power and designing power supply designs and things that chip designers are not too concerned about. But it's similar.
okay. You have to worry about how power transmits to the chips on the
Exactly.
board.
How do you get the voltage that you need and the amperage you need to specific places on the board? Uh, you know, uh, Radiating energy to space, interference from other devices in the system, these kinds of considerations. So usually chip designers are like more in their own small world inside of the packaging of the device. So they don't care that much about what's going on in the external world. But other than that, there are many similarities in terms of how you design a system.
Okay. What are some possible, when you were designing a board, what were some issues that you may find or some common misconceptions or technical issues that would arise?
I think the most challenging things that I've worked on is everything that's related to signal integrity, as it is known, getting the signals from one end of the board to the other end, being still being readable in a sense, because when you're talking about signals that, I mean, the frequencies that modern devices work on, gigahertzes, and in some cases I was working on 40 gigahertz signals, which is it's so fast, the signal gets twisted, and it gets almost unintelligible once it reaches the other side of the board. So you have to really think about how you design your system for such fast signals to actually be carried without being too warped and destroyed on the way. That's why, for example, at some point, people moved to working with fiber, with light pulses, because at higher frequencies, electricity starts displaying weird characteristics. Electricity doesn't behave, electric signals don't behave the same when you're talking about low frequencies and high frequencies. and modern technology requires really high frequencies. So I spent how many, I don't know how many months of my life trying to understand like how the world behaves when you're talking about very, very high frequency signals. It's at that point, it's less of an engineering and more of black magic. It's sometimes even called black magic because it's so much different than what we are used to. So that's a big challenge for the modern devices.
The big challenge is handling high frequency signals.
Yes.
And by black magic, you mean the fiber optic lighting transmission?
No, I mean, for example, most people don't think about it, but say you have an electronic signal which runs inside of a thin copper wire, as it does on our motherboards. We have lots of thin, very thin copper wires. At some point, you'd like that signal to, or that wire to pass through the board to the other side. Maybe there's a capacitor there, maybe there is a resistor, maybe the CPU is there. It has to pass through the board. There are specialized holes coated with metal that allow you to pass a signal through the electronic board. But once the signal changes its path and it's passing through that hole through the board, now it behaves completely different than it did when it was passing through the thin copper wire. Why? Because the geometry of the wire is now different. It was first a thin rectangular wire, and now it's a roundish cylindrical wire. That change by itself, which most of us will, I mean, most electronic designers or electronic engineers would think, okay, I mean, it's metal, metal touching metal. But no, because it has different geometry, now the electronic signal behaves differently. There are now reflections, and it can behave as an antenna for several aspects, emitting energy to space, which means you lose the energy you have on the wire itself. And these kinds of changes and ideas are quite difficult to grasp because it's science. I mean, it's basically going back to physics class, and there are no easy thumb rules to handle these situations, and that's why they are sometimes called like a black magic because sometimes you change slightly something different in the system, maybe place that hole like a millimeter from where it was before, and now everything behaves differently. Why? Magic. I don't know.
Yeah,
It's difficult.
it is difficult. And this is more applying to hardware than software, correct?
Correct. Yeah, that's totally a hardware problem, and the software world is so much easier than the hardware world. I mean, that's why you see software eating the world, as they say. That's why software is so effective, and so many people can work and create complicated stuff because software is it behaves much more rationally and as per our expectations than sometimes hardware does. Hardware is difficult.
Hardware is difficult and a lot more expensive too.
Exactly, and it takes longer because each design that I would do, you design it in the computer, you ship it to the manufacturing plant. They bring back the board itself, but that cycle would take anywhere between 3 months to a year.
Wow.
So yeah, exactly. So the debugging cycle is so slow that you have to think, you can't really start over. You have to design with fail safes and be able to change things by soldering some things on the board. So the design process is very, very slow and very, very complicated relative to working with software.
Okay. Yes. And so you eventually realized that software may even take the position with some type of algorithm being able to place the board and
Yeah, I mean it's easy. It's an easier challenge for software because I mean there are still rules governing the behavior, except that for most humans the rules are too complicated when you're talking about very dense designs, very fast designs. So I figured I'd be serving the software instead of vice versa. And I figured that when if I'll be writing the software, I'll have more space to grow as an engineer, creating more challenging designs, etc. each time. The challenge with hardware was not that interesting to me
okay. It what made it not interesting?
because at some point everything is going to be made by the design itself. All the fun part of thinking about the problem, solving the problem, is going to be done by a computer eventually, most of it. Even, I mean, think about it. Right now, we're even seeing AI systems starting to produce code, programming code. Google does stuff, and DeepMind, sorry, and stuff. And I think that probably in hardware it will be much more effective for AI to solve the challenges because humans can program pretty good, but we're not that good when it comes to hardware. I mean, that's only my idea. I don't know. Maybe other people have different ideas because it's only what I saw as an engineer myself.
Okay. Was there anything that you saw, any technology that came through your career that made you think change just, your thought process on that?
I don't know if it's a single technology. It's more like the gradual improvement of software of design systems that help you design hardware over time. I mean, even in the early 2000s, every 2 3 years we would see like a major leap in technology in terms of the systems that allow us to design analog systems, digital systems, especially analog. For example, analog. I mean, I studied analog system design. We're talking about capacitors, resistors, really analog systems like they were that were like before even before digital computers. Everybody was designing analog systems, and it is considered rather complicated. You have to write down math equations and you have to really understand what you're doing. And in all my careers and as a hardware engineer, I never designed an analog system. Everything was done by a computer. You would write down the specs of the system you needed, if it was a filter, what frequencies it needed to filter out, etc. The computer would produce a design. It will tell you what capacitors to use, what resistors, what all the other components, and you, the engineer, would only need to place them, connect them, and that's it. And that's not very interesting.
No.
That's the low level of being an engineer.
Yes. And so with that technology, I mean, we can see it. You could see it shift to board design as well.
Exactly. Yeah.
Okay. And then right after this hardware experience, did you move on to experimenting with software?
Yeah, it was actually, I was already 35 years old. I had like 10, 15, 10, 12 years experience as a hardware engineer. I studied programming, as an undergraduate, but we studied the C programming language, I remember. And C is rather complicated and it's not very friendly to newcomers.
No.
Plus, exactly, yeah. And plus, what we did in academia, was creating algorithms and you know academia stuff. And back then, I didn't see the connection between writing, bubble sort algorithm in C to creating a computer game. Yeah, I love video games, and I wanted to, experiment. How do you create a video game? But there's such a vast difference between writing a simple algorithm in C and actually having something happening on the screen and interactive designs and stuff. Back then, I couldn't close that gap in my mind, and I said to myself, that's programming. That's not interesting. That's like doing math. That's solving math equations. It's not very interesting if you're not really into it. Uh, Learning Python a long time after that changed my mindset because then I could suddenly concentrate on solving the coding challenge instead of initializing variables, thinking about memory pointers and etc. and all those stuff which is it's not a real part of solving a problem. It's just an artifact of the way C programming works. Now I'm enjoying going back to the roots and programming in C because it has lots of advantages if you really want to go to the and do interesting stuff, getting
What was
close to
that word?
bare metal. Sorry?
Antigens?
Sorry?
What was that word? Antigens?
No, no. I mean, C language is pretty interesting if you're an experienced programmer and you want to do stuff which is faster, higher performance, or like you want to do stuff in the roots of the operating system. Then C is very useful, and now I enjoy programming in C. It's fun. It's a challenge, but it wasn't when I started started learning about programming. That's why I always say that when people teach programming, they should teach programming in the mindset of a newbie, of somebody who doesn't know how to program. Handling all those problems like memory collisions and buffer overflows and all that stuff, that's interesting, but only after you know what is real programming. And it took me a long time to get to that point. But now I very much enjoy programming. I do that for fun when I'm not recording podcasts.
Oh, very nice. Do you have uh what's your favorite language right now?
JavaScript.
JavaScript?
Yeah, I mean, it's not the best designed programming language out there. Python is much better, but JavaScript allows me to do everything. I mean, I can program for the browser, I can program the backend, applications for phones. It's like a Swiss Army knife of programming languages. So I really enjoy that. I really enjoy being able to do everything in a single language.
Oh, very nice. And what are what are some examples of applications you're creating? Are you creating a website or a mobile application?
Yeah, right now because my life. I mean, 7 years ago, I quit my day job as a software engineer, and I concentrating on my podcasting career. We can talk about later if you wish. So right now, I'm programming for fun, which means I try to do things like simple computer games for the browser. At some point, I was in contact with a researcher who was studying sleeping habits in teenagers, and she needed an Android app to log sleeping hours and all those kind of variables when people sleep. What time did they go to sleep? How long did it take them to fall asleep, etc. So I designed a simple application, React application for her, which was fun. Uh, fun little projects that I do.
That is fun, and it's good to keep those skills.
Exactly. Not forget how things work.
Yes. So you also, as well as being an engineer, authored a authored a few books. What what inspired you to write books, and what inspired you to write your first book?
So actually, writing has been a passion of mine since I was like 9 years old, probably. Really, I started writing on old typewriting machines, the mechanical typewriter machines back in the 80s, before I got my first computer. And I've been writing ever since, mostly science fiction as a teenager, mostly. I read science fiction, I wrote science fiction. But at some point, I became very, very interested in technology and how things work. So, as part of my undergraduate degree as an engineer, I studied electronics engineering. I I was part of the university's magazine. I wrote for the university magazine, and came across a very interesting type of machines called perpetual motion machines, which is an impossible type of machine that can work without energy, without any energy, like a car who doesn't need fuel to run. Of course, that's impossible. But many people over the years, for the past 2,000 years, have tried to invent such machines, because there are cases in which it seems like it could be made possible if you just work on the problem and solve some little aspect of it. It's very tempting, and of course, the payoff if you create such a machine is huge. Think about it, a machine that does not need gasoline, electricity, it doesn't need anything, it just works. And I found the idea very interesting, and I decided I'll write my first real book about it. Took me 6 years of writing and researching. Yeah, it was fun, but because I was unexperienced as a writer, it was a big project. It took me a very, very long time. But the book eventually did come out. It didn't sell that much. It was people loved it, but the topic is quite esoteric in nature, so it didn't really catch on. But the experience of writing the book was fun, and I ended up writing two more books, the last of which was about the history of computer viruses. It was also the time where I began becoming more involved in software, as we spoke earlier, and the concept of self-replicating software. The earlier viruses were self-replicating. Really, I found it fascinating. So I wrote a book about the history of cybersecurity and viruses. It came out, I think, about 7 years ago. So parts of it are now, not too up to date. I need to kind of update it because lots of things have changed. But the basic ideas are still the same. Whatever happened 20 years ago, the same things are happening today. And based on that book, later I started Malicious Life, which is a podcast about the history of cybersecurity.
Okay. So that book, Battle of Minds,
Hmm. Exactly.
what got you first interested in virus or malware? And the concept of a self-replicating virus is very powerful.
It is. I think what initially hooked me on the idea was that I got a virus myself. Uh, it was back, I think, in the maybe 2004, 2005. It was called Blaster, and it was a worm that caused the computer to shut down, count down 60 seconds, and then shut it down. That was it wasn't meant to do that. It was a bug of the design. The virus author made a mistake, but that's what ended up happening. You booted the computer. There was an error message. Your computer will be shut down in 60 minutes, 60 seconds, and you've got 60 seconds to figure out what's wrong, and then the computer shuts down. And it took me quite a lot of boot cycles, 60 seconds each to figure out what to do. And that experience got me thinking about what kind of software can infiltrate, so to speak, a computer and cause it to do stuff. It was not the software that I was used to. I mean, most of the software I was working with is a software that serves you as the user. It works for you. And here's like an alien piece of software that somehow infiltrated the computer, and it got my imagination working because we know biological viruses. The idea is quite similar. A biological virus entering the body from outside, hijacking cells, making them do stuff. And I got interested in the idea of a digital virus, what that is. Started researching it. Took me a while to actually sit down and write a book about it. But once I did, I realized that actually the technological aspect of cybersecurity is only half of the story. The other half is the human machine interface, the psychology of the writer, the malware authors, the defenders, the users, when you were talking about, say, things like social engineering. So there's lots of human psychology aspect of cybersecurity, and and for me, as someone who is very interested in also in human psychology, I also very much interested in biological systems and the human mind, etc. It was a very interesting a place, a point of contact between these two seemingly very different worlds. And once I dug deeper into cybersecurity, I found lots and lots of similar ideas, places where the human and machine aspects of the story come together. That's, I think, what makes cybersecurity such a very interesting topic in general, even for engineers in the topic. They have to think about not just the machine, but there's a human on the other side. That's why I called the book Battle of Minds. It's a battle between two humans using autonomous software systems. Very interesting basic idea, I think.
It's a very interesting idea. The what did you find in your writing that book? What were some things that you learned that you hadn't really known before?
Good question. Um, I think it changed the way I perceive the internet, basically. Um, Up until that point, for me as a user, the internet, the wild, the global connection of networks was really transparent. We sit in front of our computers, we press a link, YouTube opens or whatever, and we're using the software, engaging ourselves with the software. But learning about cybersecurity means that all of a sudden you have to really take into consideration how the internet works, how the actual hardware of the internet operates, who controls it, uh, how things are determined, and who gets to decide about what kind of data can move around. And it really made me think about global networks differently. They have their own network effects, and the way you construct a network really impacts how designs are done based on that global network. Um, it really made me go deeper in the software stack. Most programmers, they stay within their device. I mean, if you're programming for a smartphone, you stay within the confines of the model of the smartphone in your mind. But when you're thinking about viruses, you're thinking about worms, DDoS attack, these you also program the virus, the malware, but then you release it to the wild, and it does things in the wild. It passes through other networks, it goes into other devices. Everything interacts with everything else. For example, I mean, there's one famous example of the very one of the very earliest viruses, the Morris worm. I think I told that story in one of the earlier episodes of Malicious Life. It's a virus from 1988. It's a worm that did lots of damage. In the infant internet, it was then very in its infancy, and the way the worm propagated means that there were many more copies of the worm in the world at the same time than the virus author even dared to imagine, which caused lots of congestion problems on the network and stuff, because the virus author was focused on making the software work on the destination machine, the target machine, but he didn't think about the network aspect of it, and ended up creating a malware that was replicating so fast and in so many cycles at the same time that each target machine was attacked by thousands of copies of the same worm. So that's a totally different engineering problem, creating one worm as opposed to creating a worm that interacts with all the other worms in the world. it's, you have to think differently. It's very interesting.
Absolutely think differently. It's very distressing to receive a worm.
It is, yeah.
And as you said, our relationship, you said you changed your relationship with the internet, and in 1988 with that, what was that worm called?
Morris worm,
Morris worm?
named after the guy who wrote it, Robert Morris.
Was it was that malicious? Was that intentional, or was the large amount of copies unintentional?
No, unintentional. What Morris wanted, and by the way, that specific Robert Morris, he became, I mean, he was a good guy in essence. He didn't want to cause harm. He later went on to found Y Combinator, a very famous VC fund in California. He wanted to experiment with creating malware, but it was supposed to be harmless. The way he thought about it, it should have been harmless. But as we said, because he probably didn't understand how big the internet is, the way he programmed his malware to work would have worked if the internet was, a few hundred machines connected. But even in the 1980s, there were already tens of thousands of machines connected in the United States alone. And that made the worm replicate in much larger quantities than he imagined, which caused network congestion and load and caused high loads on the CPUs of the computers that ran those malwares, and everything came down crashing. And that was the problem. If he didn't mean it to be so destructive.
Wow. And now we have not just computers on the internet, but we have phones, we have televisions. Malicious Life had an episode on smart televisions, and
Right.
it it goes to show you, that, and even like anything we interact with is, anything smart is on the internet, and there's a possibility that a virus could transmit into that device.
Exactly, and I think that's a very interesting aspect of the how can I define it? Maybe the ecosystem, the digital ecosystem. I mean, think about it that now we've got a global network which is on 24/7. There's always activity going on in the network. So malware, all sorts of malware, some of them never really die out. They can always find some host in that vast and big network. So you've got right now worms and viruses and malwares that were authored like 15 years ago, 12 years ago, still active on the network. And because, as you said, we've got new devices continually getting connected to the network, lots of different operating systems. So it's like the ecosystem is getting more sophisticated. It used to be only Windows and only PC computers, maybe, or like, homogeneous environment. Now, as the days goes by, the internet is becoming heterogeneous. Lots of different machines, different applications. Everything is being connected. And I think that kind of it starts behaving more like biological ecosystems at that point. Maybe not today. Maybe we're only getting to that point. But if you have so many different softwares and malwares and devices and operating systems and data flowing inside of a global ecosystem, which is always on, lots of interesting things happen. Um, and especially if you're talking about self-replicating programs, which once you release them to that environment, they never die off, which is really interesting to think about it. It's like the same way that if you look into your average, you look at the palm of your hand in a microscope, you'll see bacteria and viruses on it. It's always there. Same with our network. And at some point, I think will be forced to look on the global network as if it's a biological environment, and biological rules will apply to it in a sense. That's kind of science fiction thinking, but you have to look a few more years into the future. The network is not a passive part of technology. It's getting to be an ecological system of its own, right? As we release more and more sophisticated software on it. Think about AI. AI is going to be much more autonomous. It's already autonomous in many of the things it does. It communicates autonomously. Once it can evolve, once AI systems begin to evolve themselves and change as they operate and learn new stuff, and that's right around the corner. People are doing interesting stuff right now. I think our digital lives are going to be even more interesting in the future.
Absolutely. It more interesting. Do you think more complex?
Uh, that's also a good question. I think that if looking back at what we had 20 years ago, there's no doubt that things are much more complex now. Uh, as we said, many more devices, different types of devices, many different applications that people run on the internet. Back then, we only had what? Email, maybe file sharing, and websites, whatever. Now we've got smartphones and video, and I mean, we've got so much stuff going around. So everything is much more complicated, but we have better tools. We grew up with that environment. So most of us don't think of it as being more complicated. It's just what it is. If we look in the future, I guess it's going to be the same type of thinking. People won't really think about that connecting fabric of the internet too much, but the software itself is going to be so much more evolved that I think we will start to see more autonomous software handling stuff inside the internet. It's going to be an ecosystem of itself at some point. Uh, it's something that's really interesting. I hope I'll live to see that much advancement in electronics.
What when you say it mimics a biological system with heterogeneous components and it may become its own ecological environment, what are some things that you envision, and what, yeah, I guess what would be what you envision when you say that?
Let's think um, about worms, computer worms, for example. Computer worms, for your listeners, for your viewers, if they don't know the term, is software that is able to propagate via networks. It goes from a machine to a different machine via the network. And it's usually autonomous. It can self replicate and move to another network without human intervention. Let's imagine such a software being able to um, evolve itself and start attacking or targeting different operating systems. Right now, if you're writing a worm malware, for example, you have to write it for to run on Windows or Android or iOS. You have to decide what kind of machine you target. Once these software systems will get, those malwares will get to be self-evolving in a sense, which is, I think, not too far in the future, then think about the adversary in that case for cybersecurity specialists, for the people who defend against cyber. Right now, our adversaries are the quote unquote bad guys, the malware authors, the people who write malware and try to steal money, to hack, to breach, whatever. Think about what will happen once those malwares are so advanced, they start working for themselves. Much like how biological viruses work. I mean, biological viruses are not alive in the normal sense of the word. They can't really live by themselves. They need the biological host, the cell host, to enable them to replicate and propagate. I'm guessing that worms still need our machines to replicate, but now they are evolving. In that scenario, they are evolving by themselves. So it's, you're not, as the defender, you're not defending against another human, but defending against a self-improving AI system. And that's a completely different challenge. It's much more it's closer in nature to the way we try to fight bacteria and biological viruses that are also autonomous and self-replicating, and they evolved themselves to fight our antibiotics, to try and fill ecological niches that are they were not filled before. Once that happens in cybersecurity, challenge is going to be completely different. The time limit, I mean, right now, you do something, the human adversary at the other side maybe it takes a few days, they do something else, and you respond, etc. What happens when software is self evolving? All those modifications will take seconds, you know, thousands of seconds, one tenth of a second sometimes. So you have to design an AI system to enable you to defend against that other AI system. And that raises the battle of minds, so to speak, to a totally new different. Now you have two autonomous systems working once one against the other in in the quote unquote darkness of the web, like two bacteria fighting on the same ecological niche, maybe evolving attacks and defenses all by themselves. It's a very exciting concept. It's very science fictiony, but I don't think we're too far away from it once I see computer software being able to to program new software. And that's what we are seeing in the past 2 years. It's happening right now.
Wow. And when you say that, one autonomous system against the other autonomous system, I'm thinking of the immune system against a replicating virus.
Exactly, exactly. I mean, we ourselves are only biological systems. We are ourselves evolving all the time. Um, I think the analogies here between the electronic or the digital and the biological are at some point of complexity, at some level of complexity, they become identical. It's just the different substrate, the different ecological environment that the creature lives in, but the rules governing its behaviors and complexity and evolution are relatively the same. So at some point, technology becomes biology. Interesting.
Very interesting. And do you think that self-replicating virus may be a result of a developer losing control of a software?
I mean, he or she would have to design it to be self-evolving. I'm guessing that it is not something that will happen spontaneously. It will have to be designed that way. But yes, there is the possibility that once you design such a system and you release it in a certain environment, maybe your own network, things happen, accidents happen, it can escape. Much like, a biological virus can escape from a lab when somebody is experimenting. I'm guessing that most researchers, most people who write it will try to control their design, but at some point you can't because of all the unintended network effects. There's a very interesting story, for example, about one of the very early worms in the late 70s. Xerox Labs. Xerox Labs was a hub of, of, um, of innovation back in the 70s. And they experimented with self replicating worms, which was a radically new idea back then. And they tried to, and there were a couple of researchers there who tried to use those self replicating worms for good intentions, for practical intentions. For example, they had an idea that they had, like, an office building, and all of the employees would go at evening. All the employees would go home, and there were all those computers sitting at their offices doing basically nothing. Some of them were on, but they were doing nothing. They had the idea that if they could create quote unquote a good worm that would replicate between in the network between those the computers in the office building, they would be able to use it for rendering graphics or solving complex mathematical equations, because now you have lots of computer power at your service. But what they didn't take into account that sometimes there are errors, and the worm got out of hand, and it replicated much faster than they expected, and it started crashing computers at various places in the big office building. And at some point they had to shut the entire facility basically and reboot all the computers, because they didn't take into consideration that bugs can happen, machines can crash. It's not all machines behave in a similar way. So once you go, I mean, the designer of the malware will probably be thinking about their own computer, their own environment. Once you release that software to the wild, it can encounter vastly different conditions, vastly different types of machines, of other software it will work against. If it at that point it can evolve, it will evolve in unexpected directions. That's how biology works. That's how you get the variety of creatures we have around us in the biological world. So it will start with good intentions, probably. Nobody will think about releasing it and be having it do whatever it wants. But I'm guessing that at some point the complexity will take it out of our hands. I guess.
Okay, similar to the situation at Xerox where they wanted a good virus, they wanted it to do positive things, but it's a
Exactly. It ended
self-replicating.
up crashing computers. Yeah.
Wow. Well, we'll see how the network progresses. So to change topics, you alluded to this earlier that you left engineering professionally to be a podcast host, and y- you are the host of Malicious Life podcast. But that wasn't the first podcast you created. You created Making History in
Correct.
2007.
Correct.
What, so 2007 is very early for podcasting. What is what got you motivated to create Making History?
So back in even 2005, I first learned about podcasts. Just as a regular listener, wanted to listen to interesting stuff. Back then, we didn't have smartphones yet. The iPhone only came out, I think, in 2007. And listening to podcasts was much more of a challenge in technical terms. You had to install software on your PC, download, find podcasts somehow, download MP3 files, transfer them to, maybe a small device that you could hook your headphones to, whatever. So it was a challenge. Almost nobody listened to podcasts back then. But because I was an engineer and I wasn't afraid of technology and it wasn't a big challenge for me, I knew computers. So I enjoyed it. I listened to lots of podcasts. And at some point, a friend of mine who was also a podcast listener, I think it was early 2007, suggested we do a podcast together about computer games, which we both loved. And I said, you know what? Interesting. I've never in my life was in a radio studio, and I never actually did any, radio stuff. I never talked in front of the microphone. But why not? I mean, it's fun. It should be fun. So we started a podcast about computer games, and we did that for about half a year or so. It was great fun. I learned how to edit sound and how to put up an RSS feed for to work with iTunes and stuff. And I kind of got the hang of how to create simple podcasts. And it probably is somewhere in like the middle of 2007. I thought to myself, you know what? You love to write books about the history of science and technology. Why not start a podcast? And I was certain that nobody will listen to a podcast about the history of science and technology because computer games are much more fun, much more interesting. And I thought, I mean, that's probably just it's something that I enjoy, but there are like probably 10 or 20 people in Israel who enjoy that kind of content. But I said, okay, so I'll just do it for fun. But when I started making history, I was really surprised to learn that a lot of people were interested in those topics. So the podcast started growing, and it started growing much faster than the podcast the original podcast about computer games. Plus, I had the good fortune of the iPhone being released that same year, and then smartphones getting into the market at 2008, 2009. Applications started appearing that allowed people to listen to podcasts with their smartphones. So I was at the right time with the right kind of the right kind of podcast that people would really like to listen to. And so making history exploded. It became the biggest podcast in Israel. And it was so for at least 10, 12 years with hundreds of thousands of listeners. And of course, you probably hear that these kinds of stories every once in a while of somebody who releases a viral video and it kind of turns their world around. They, their lives change completely. That's my case. At some point, the podcast became so popular that I had to decide what I'm going to do with my life. Am I going to be an engineer? Because back then I was an engineer working, 9 to 5, doing what everybody was doing. And at night, I was a podcaster who was kind of semi famous at that point within listening podcast listeners in Israel. So at some point, 7 years ago, I decided, okay, I need to decide what I want to do with my life. And I took the plunge. I quit my day job, got a partner, a business partner. We raised money, started a podcasting production company. And right now, in 2022, we've got well over 60 podcasts in Hebrew and English, working with tens of different podcasters around the world and in Israel, creating all sorts of content. I'm the executive editor of that network, so I get to decide on the direction and the type of content that we create. And I think it was 5 years ago or 4 years ago that we were approached by Cybereason, who is a cybersecurity company. I think their CEO and his co-founders were listeners of Making History because the founders were Israelis. They spoke Hebrew. And they approached us and said, we want you to create a podcast about cybersecurity, which will be like Making History that you have in Hebrew. A narrative, story based show, highly researched and fun to listen to. Not very overly technical, but it needs to have some level of technical understanding to teach the audience interesting stuff. And it was a great challenge because writing about technology in a way that will be engaging and fun is something that I think very few writers or podcasters can do. You need to understand both the technology and how to create a good story. It's not an easy thing. Most writers are not very technical people. They are humanists. They learn literature and English literature and stuff. Not a lot of engineers go to writing. So that was actually, I think, another good, lucky strike for me, because as an engineer who can also write and tell good stories, I was at the right time in the right place. And so Malicious Life rather quickly became popular. I think right now it's probably the second most listened to podcast in the world about cybersecurity, after Darknet Diaries, which is a fantastic, phenomenal show, and it's fun. It's a great adventure for me. I mean, I started in Israel as a small time podcaster, and now back before COVID-19, we had listener meetings in Las Vegas, where I met listeners from all over the world. India. South America, lots of Americans, Canadians, Europeans. It's a huge adventure. It's amazing.
That is amazing. And it's been listening to Malicious Life over the last year, 2 years has been invaluable to my development as a cybersecurity professional.
Well,
So
so
thank you.
I'm so happy to hear that.
And so
And
how
I should also probably mention, it's very important, I think, that I no longer work on Malicious Life by myself. I used to write all the episodes by myself and do all the sound editing and everything from scratch. Now that the company has grown and I was able to hire, excellent producers, excellent writers, people who work with me. For example, Nate Nelson, he's a senior producer on the show, and he's a gifted writer. And it's, I mean, finding people in his caliber has been a great addition to the show. So now I can do even better stuff. I can do more shows and talk about topics which I couldn't in the beginning.
That's exciting. So the development has gone very well over the last 7 years. You
It
were
is.
able to connect with Cyber Reason, and you were able to bring on individuals who have high, you know, good skills that really bring high value.
Yeah. Right now in my network, in my podcasting network in Israel, we've got lots of people who are, television personalities, radio personalities, people who create in all sorts of different kinds of content. And it's very exciting for me to work with, professionals, because if you remember at the beginning, I told you before podcasting, I was never on TV. I was never stepped inside of a radio studio. So I'm an outsider to that world, to the old traditional media. I'm a real outsider. And now being the executive producer of people of that caliber, it's a very learning experience for me. I have to learn how television works, how movie making works, because now the media, you can't just stay in podcasting and that's what you do. You have to pay attention to what all the other, YouTube is something very interesting. TikTok is very interesting. You have to think more broader than just in podcasting. So it's a very interesting experience.
That is very interesting. I wish the best of luck to you with that.
Thank you.
So, Rand, do you have any last words or any things that you'd like to say to the audience about podcasting or writing or creating, even cybersecurity or anything we've spoken about?
Um, I think what helped me the most across the years is my curiosity. I'm a very curious person. I always want to learn how things work in the most basic level I can, and it's a personality trait, from being a kid. It's always been there with me, and I think that that's something that really helped me along in my career, because we live in a world which is changing drastically. I mean, the world as it was 20 years ago is very different than it is now. Lots of new opportunities are always presenting themselves. New websites, new services, new programming languages, new medias. Everything can, from one year to the next, lots of new opportunities can arise. Who are the people who enjoy these kinds of changes? Are the people who are curious at heart and want to learn new stuff, because then they expose themselves to all those interesting opportunities. Uh, Say, for example, that you're a programmer and you're used to writing in JavaScript. That's what you do in your day job. That's what you do. You're an expert in JavaScript. But we know that every 5, 6, 7 years, a new programming language comes around, or it might be a new computer, Or maybe now there are quantum computers that are popping up and we're starting to hear about it. If you're not curious, you will stay inside your lane, in your protective shell. You will do your day-to-day job, but you will not have the opportunity to seize other new exciting ideas and make them work for you. So what I would advise our listeners, if someone is cares to listen, is always provide a place for your curiosity to grow, to work, to do its work. For example, me as an engineer, I would dedicate the first half hour of each workday, no matter what I was working on, half an hour of diving deep into the basics of the project I was working on. If I was working with certain device, most engineers would only read the manual, for example, of how it works and what you need to do with it. In that half an hour, I would go deeper. I would find the technical articles of how it works, in the deepest levels, which are unneeded in day-to-day job. But every once in a while, that kind of curiosity and digging would would allow me to discover something new, as it was with programming, as it was with FPGA that I discovered, which was with podcasting that I discovered because I was curious. And it gives you new opportunities which can take your career to successful new heights and very unexpected directions. So curiosity for us humans is a very effective driving force. Give it its place. Give it the sunshine it needs to grow and evolve, and it usually will take you to grow to great places.
My guest today has been Ran Levy. Thanks for coming on the podcast, Ran.
Thank you very much, Kush.